Hello, myself Dr. BJD Kalyani, working as Associate Professor in the Department of Computer Science and Engineering of Institute of Aeronautical Engineering. In this video, I will discuss the practice problems related to input-output organization. For the computer to interact with the external environment, input-output devices can be preferred. The peripheral devices provide man-to-machine interaction and machine-to-man interaction. So, various peripheral devices can be used, for example, keyboard, mouse, and also the printer, scanners. All these are variety of input-output devices. So, here the communication between the input-output devices and the central processing unit can be synchronized with the help of input-output processor. And the mode of communication can be generally the synchronous or it may be asynchronous. So here how the access time of devices can be calculated and how asynchronous communication bits are incorporated, those problems can be discussed in this video. The first problem statement is, consider a disk pack with the following specification: 16 surfaces, 128 tracks per surface, 256 sectors per track, and 512 bytes per sector. Answer the following questions. What is the capacity of disk pack? What is the number of bits required to address the sector? If the format overhead is 32 bytes per sector, what is the formatted disk space? If the format overhead is 64 bytes per sector, how much amount of memory is lost due to formatting? Next question is, if the diameter of innermost track is 21 centimeters, what is the maximum recording density? If the diameter of innermost track is 21 centimeter with 2 kb per centimeter, what is the capacity of one track? If the disk is rotating at 3600 rpm, what is the data transfer rate? If the disk system has rotational speed of 3000 rpm, what is the average access time with a seek time of 11.5 milliseconds? So these are the questions. So here the data that is given in the problem is, a disk pack of total number of surfaces are 60, number of tracks per surface is 128, number of sectors per track is 256, number of bytes per sector is 512 bytes. So generally the disk can have the surface. So here it is the spindle. Total like this surfaces, 16 surfaces, disk surfaces are here for a disk pack. And the spindle is attached with a read-write head. When this head touches the magnetized surface of the disk pack, the read or write operation can be performed on the disk surface. So if you consider a single disk surface, the disk surface can consist of concentric circles. Those circles can be called as tracks. And tracks can be further divided into parts. Those parts are known as sector. So here there are 128 tracks for the disk surface and number of sectors is 256 and the number of bytes per sector is 512 bytes. So this is the disk pack architecture. So first problem is to find the capacity of the disk pack. The capacity of a disk pack can be calculated with total number of surfaces multiplied by number of tracks per surface multiplied by number of sectors per track multiplied by number of bytes per sector. So, in the problem, 16 disk surfaces are available. Number of tracks 128 multiplied by 256 is the number of sectors, and in each sector 512 bytes is the capacity. So, multiplying all, we can get 228 bytes. So, it is 256 megabits. Next problem statement is number of bits required to address the sector. So, total number of sectors is equal to total number of surfaces multiplied by number of tracks per surface, number of sectors per track. So, 16 into 128 into 256. So, it is equivalent to 2 power 19 sectors. So, 19 is the 2 power 19 is used to map the address space. So, here we have to require 19 address lines in order to point a address in the sector. Next, formatted disk space. The formatting overhead can be calculated with the total number of sectors multiplied by overhead per sector. So, total number of sectors 2 power 19 multiplied by 32 is the overhead per sector that is given in the problem. So, it can be represented 2 power 19 multiplied by 2 power 5. So, total 2 power 24 bytes. So, 16 megabyte. Now, formatted disk space can be total disk space minus the formatting overhead. The total disk space can be the 256 MB and 16 megabits is the overhead. So, 240 MB is the formatted disk space. Next, what is the formatting overhead? Amount of memory lost due to formatting is generally referred as the formatting overhead, and it can be calculated with total number of sectors multiplied by overhead per sector. So, 2 power 19 multiplied by 64 bytes. So, it can be 2 power 25 bytes. So, 32 MB is the formatting overhead. Next problem is maximum regarding density. So, storage capacity of a track can be calculated as number of sectors per track multiplied by number of bytes per sector. So, 256 multiplied by 512. So, 2 power 8 multiplied by 2 power 9. It can be 2 power 17 bytes. 128 kilobytes is the storage capacity of one particular track. So, circumference of the innermost track can be calculated with 2 pi r. So, pi into diameter. So, here 3.14 into the diameter can be 21 centimeters, that is given in the problem. So, 65.94 centimeters is the circumference of the innermost track. What is the maximum recording density? Maximum recording density is recording density of innermost track. So, it can be calculated by capacity of a track divided by circumference of innermost track. The capacity can be 128 kb that we calculated in the previous problem statements. And circumference also we calculated in the previous slide, 65.94. So, 128 kb by 64.94, that is 1.94 kilobytes per centimeter is the maximum recording density. Next, what is the capacity of a track? Circumference of innermost track, which can be calculated with pi into diameter. So, 3.14 into 21 centimeters. So, that is 65.94 centimeter. So, the capacity of track can be calculated with storage density of innermost track multiplied by circumference of the innermost track. So, 2 kb per centimeter multiplied by 65.94 centimeters. So which can be 131.88 kb, which is 132, approximately 132 kb. Next, what is the data transfer rate? So number of rotations in 1 second. So here RPM can be calculated 3600 by 60 rotations per second. So 60 rotations per second is the number of rotations per second, which is given in the problem in the minutes RPM, that is converted into the seconds. Now data transfer rate is number of heads multiplied by capacity of one track multiplied by number of rotations in 1 second. So 16 multiplied by 256 into 512 bytes multiplied by 60. So which can be represented with 2 powers. So 60 multiplied by 2 power 21 bytes per second. So it can be the 128 Mbps, megabits per second. Next, what is average access time? Time taken for one full rotation is the first we have to calculate. So 60 by 3000, which can be the 0.02 second, 20 milliseconds. Average rotation delay can be half of the time taken for one full rotation. So half into 20 milliseconds. So it can be 10 milliseconds. Now we have to calculate average access time. Average seek time plus average rotational delay plus other factors is the average access time. So average seek time is 11.5 milliseconds and average rotational delay 10 milliseconds. No overhead or other factors are there, so it can be 0. So the answer can be 21.5 milliseconds. The next problem statement is, what is the average access time for transferring 512 bytes of data with the following specifications? Average seek time is equal to 5 milliseconds, disk rotation 6000 RPM, data rate is 40 kilobytes per second, controller overhead is 0.1 millisecond. So the parameters that are given in the problem is average seek time 5 millisecond, disk rotation 6000 RPM, disk rate 40 kb per second, controller overhead 0.1 milliseconds. So time taken for one full revolution is 60 by 6000 seconds. So it can be the 10 milliseconds. Next, what is the average rotational delay? Which can be calculated with half into time taken for one full revolution. So it can be half into 10 milliseconds, so 5 milliseconds. Next, what is the transfer time is 512 bytes by 40 kb. So here the 512 bytes is the access time for transferring 512 disk data. So the 512 bytes by 40 kb, so it can be 12.5 milliseconds. Next, average access time is equal to average seek time plus average rotational delay plus transfer time plus controller overhead plus queuing delay. So here 5 milliseconds plus 5 milliseconds plus 12.5 milliseconds plus 0.1 milliseconds plus no queuing delay, so it can be the 0. So total it can be 22.6 milliseconds. Next problem statement is, a certain moving arm disk storage with one head has the following specifications. Number of tracks per surface is 200, disk rotation speed is 2400 RPM, track storage capacity is 62,500 bits, average latency is p milliseconds, data transfer rate is q bits per second. What is the value of p and q? So you have to find out average latency and data transfer rate. So the parameters that are given in the problem is number of tracks per surface is 200, disk rotation speed is 2400 rpm, track storage capacity is 62,500 bits. Time taken for one full rotation is 60 by 2400 seconds. So 1 by 40 seconds, 0.025 seconds. So 25 milliseconds is the time taken for one full rotation. Now we have to calculate average latency. Average latency or average rotational latency is half into time taken for one full rotation. So half into 25 milliseconds, 12.5 milliseconds is the answer. So it is the P value. So P is the average latency. Next, data transfer rate. The data transfer rate is equal to number of heads multiplied by capacity of one track multiplied by number of rotations in 1 second. So 1 into 62,500 bits into 2400 by 60. So it can be 2.5 into 10 power 6 bits per second. It is the Q value. So in the problem we have to identify the P and Q. P is 12.5 and Q is 2.5 into 10 power 6 bits per second. Next problem statement is a disk pack has 19 surfaces. Storage area on each surface has an outer diameter of 33 centimeters and inner diameter of 22 centimeters. The maximum recording storage density on any track is 200 bits per centimeter and minimum spacing between track is 0.25 millimeter. Calculate the capacity of disk pack. So here in the problem, the number of surfaces is 90, outer diameter is 33 centimeters, inner diameter is 22 centimeters, maximum recording density is 200 bits per centimeter, inner track gap is 0.25 millimeter. So number of tracks on each surface can be calculated. Outer radius minus inner radius by inter-track gap. So 16.5 centimeter minus 11 centimeters by 0.25 mm. So it can be the number of tracks can be 220 tracks. And capacity of each track can be calculated. Maximum recording density multiplied by circumference of innermost track. So 200 bits per centimeter multiplied by 3.14 into 22 centimeter. So which can be 13,816 bits. So 1727 bytes. Capacity of disk pack can be calculated with total number of surfaces multiplied by number of tracks per surface multiplied by capacity of one track. So 19 into 220 into 1727 bytes. So it can be 6.88 MB. Next problem statement is consider a typical disk that rotates at 15,000 rpm and has a transfer rate of 50 multiplied by 10 power 6 bytes per second. If the average seek time of the disk is twice the average rotational delay and the controller transfer time is 10 times the disk transfer time, what is the average time to read or write a 512 byte sector of the disk? So here in the problem, the parameters that are given is rotational speed of the disk is 15,000 rpm, transfer rate is 50 into 10 power 6 bytes per second, average seek time is 2 into average rotational delay, controller's transfer time is 10 into disk transfer time. Time taken for one full rotation is 60 by 15,000 seconds. It can be 4 milliseconds. Average rotational delay can be the half of the time taken for one full revolution. So it can be half into 10 milliseconds, 2 milliseconds. Average seek time is calculated with 2 multiplied by average rotational delay. It can be 4 milliseconds. What is the data transfer rate? The data transfer rate is time taken to read or write 512 bytes. So here the 512 bytes by 50 into 10 power 6 bytes per second. So it can be 0.01024 milliseconds. So controller's transfer time is equal to 10 into disk transfer time. So 10 into this, the transfer time can be multiplied. So the answer is 0.1024 milliseconds. And what is the average time to read or write 512 bytes? Average seek time plus average rotational delay plus disk transfer time plus controller transfer time plus queuing delay. Here no queuing delay, it can be 0. Remaining all parameters we have calculated in the previous slides. So those can be added. So we can get the answer 6.11 milliseconds. Next problem statement is, a hard disk system has the following parameters. Number of tracks 500, number of sectors per track 100, number of bytes per sector 500, time taken by the head to move from one track to another adjacent track is 1 millisecond, rotational speed is 600 rpm. Then what is the average time taken for transferring 250 bytes from the disk? So the values that are given in the problem are number of tracks 500, number of sectors per track 100, number of bytes per sector 500, time taken by the head to move from one track to the another adjacent track is 1 millisecond, rotational speed is 600 rpm. So average seek time is equal to time taken by the head to move from one track to another adjacent track plus time taken by the head to move from track 1 to the track maximum track is 500 by 2. So it can be 0 plus 499 into 1 millisecond by 2. So the answer is 249.5 millisecond. Next, time taken for one full rotation is 60 by 600. So it can be the 100 milliseconds. Average rotational delay is equal to half into time taken for one full rotation. So it can be 50 milliseconds. Capacity of one track is equal to number of sectors per track multiplied by number of bytes per sector. So 100 into 500 bytes, 50,000 bytes. Data transfer rate is calculated with number of heads multiplied by capacity of one track multiplied by number of rotations in 1 second. So it can be 1 into 50,000 bytes multiplied by 600 by 60. So it is 5 into 10 power 5 bytes per second. So what is the transfer time is 250 bytes by the data transfer rate. So it can be the 50 multiplied by 10 power minus 5. So 0.5 milliseconds. Next, average time taken to transfer 250 bytes can be average seek time plus average rotational delay plus transfer time plus controller overhead and queuing delay. In the problem, no controller overhead, no queuing delay is mentioned. So those two parameters can be taken as 0. Remaining all we calculated in the previous slides. So all can be summated. The answer can be 300 milliseconds. Next problem statement is, in a 4 megabit chip organization has a total of 19 external connections. Then it has a dash address and 8 data lines are there. So we have 8 data lines and 19 external connections it has. So it can have the 9 address lines. It is a 512 by 8 organization. 2 power 9 is 512 and the data lines is, the address space is 512 and the data lines are 8. Next, how many characters per second can be transmitted over a 1200 baud line in each of the following modes? Assume a character code of 8 bits has to be transmitted. First problem statement is synchronous serial transmission. Second one is asynchronous serial transmission with 2 stop bits, asynchronous serial transmission with 1 stop bit. So here, in case of synchronous serial transmission, 1200 baud lines. So 1200 by each character can be represented with 8 bits. So with synchronous serial transmission, 1200 by 8, 150 character per second CPS can be transmitted. In case of second one, asynchronous transmitter with 2 stop bits, 1 for clock and 2 for 2 stop bits. 8 plus 3, 11, 1200 by 11, 109 CPS. The third question is asynchronous serial transmission with 1 stop bit. So 1 for clock, 1 for stop bit. So 8 plus 2, 10. So 1200 by 10, 120 CPS is the answer. Next problem statement. What happens in the daisy chain priority interrupt when a device 1 requests an interrupt after device 2 has sent an interrupt request to the CPU, but before CPU respond with the interrupt acknowledge? So first initially device 2 sends an interrupt request. Okay. So device 2 priority in, priority out can be 0 and RF is equal to 1. Why? Because this device can raise the interrupt. Device 1, all parameters can be 0. Before CPU responds with acknowledge, device 1 sends the interrupt request so that the RF value of device 1 can be 1 and device 2 can also be 1. After CPU sends an acknowledge to the device 1 has the high priority. So it is the priority interrupt problem. 2 interrupts can be raised simultaneously. Then CPU decides to acknowledge the interrupt which is having high priority. So device 1, device 2 both are raised the interrupts. CPU, depending upon the daisy chain, the CPU can prioritize device 1 having the high priority and acknowledge with a VAD enable is 1. Next, a DMA controller transfer 164-bit words to memory using cycle stealing. The character words are assembled from a device that transmits character at a rate of 2400 per second. The CPU is fetching and executing instructions at an average rate of 1 million instructions per second. By how much will the CPU be slowed down because of the DMA transfer? So CPU refers to the memory an average of once every 1 microsecond. Okay. Next, characters arrive at every 1 by 2400, so 416.6 microsecond. So 2 characters of 8 bit, each are packed at 16 bit word. So 2 into 1 character rate is 416.6, so 8.3 microseconds. So the CPU has to be slowed down not more than 1 by 833.3 into 100.12%. Next problem statement. The address of a terminal connected to a data communication processor consists of 2 letters of the alphabet or a letter followed by one of the 10 numerals. How many different addresses can be formulated? So there are 26 alphabets and 10 numerals. So 26 into 26 plus 26 into 10. So 936 possible addresses can be used. So In this video, I have discussed the problems that are related to the input-output organization that are specified and referred with the textbook of Computer Systems Architecture by Maurice Mann. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.